Hello, this is the first of the differential equations review lectures for the Quantum Formalism Quantum Materials course. I'm Thomas Silverman. In this lecture, I'll be giving an overview of differential equations and also how to solve some first-order ordinary differential equations. All right, we'll start out with some terminology. So first, an ordinary differential equation is a differential equation where the unknown function you're trying to find is of a single variable. So with a differential equation, as you can see over here, you have some unknown function, in this case v, which you might think of as velocity of some object as a function of time t. G, m, and gamma are all constants, and you're trying to solve for v as a function of t, and you have some equation that also involves its derivative, or it might involve some higher derivatives as well. And that's a differential equation, and your goal is to try to find an unknown function so that when you plug it into this equation, including taking derivatives, the equality is satisfied. Okay, so partial differential equations come up in physics quite a lot as well, especially in quantum mechanics. You have the Schrödinger equation and also the wave equation is another common one. There's lots of partial differential equations that'll show up in physics. We won't be covering any of those in these lectures, though. We'll be focusing on the simpler case of ordinary differential equations. Another piece of terminology is the order of a differential equation, and that is the order of the highest derivative that shows up in your differential equation. So this one I have over here would be a first order differential equation. It only involves a first derivative and not a second derivative or anything higher. In these lectures, we'll mainly be focusing on first order and second order differential equations. Okay. And another piece of terminology is to say whether a differential equation is linear or not. So if you write your ODE as collecting everything onto the left-hand side, you can write it as some big function, capital F, of t, y, and all of the derivatives, set that equal to 0. And we'll say that ODE is linear if this function, capital F, is linear as a function of y and all the derivatives. It does not necessarily have to be linear as a function of t. So as we see in these examples, okay, so first that object falling under the influence of gravity with some air resistance, this first equation ends up being first order and linear. As I said, the g, gamma, and m are all constants. And so we have some constant multiple of v here. This is just 1 times dv dt. So those would be, for example, those would be playing the role of y and y prime in the previous notation. And so that's all fine. So we have a linear function. If you brought everything all over into one side, you'd have some big linear function of everything. And as we said before, it's first order because it only involves a first derivative. All right, the second one would be third order because you have a third derivative showing up as the highest order derivative there. This one's also linear. So even though you have this t to the fourth over here and an e to the t as a coefficient of the second derivative, that's okay because it does not necessarily need to be linear as a function of t. And finally, for this third one, this would be a differential equation describing the motion of a pendulum with no friction. So here you're looking at the angle theta that this pendulum is making with its equilibrium to be hanging vertically. And here this one is second order because it involves a second derivative of theta, but it's nonlinear because here you have sine of theta. Here theta is the dependent variable. It's playing the same role as y in the earlier notation. That is not a linear function of theta. You have a sign there. Okay. So some questions in setting differential equations that you might want to think about. Do solutions exist? So if you can write down this equation involving an unknown function and its derivatives, but can you actually find anything? Is there anything that actually satisfies that? And another important question is, if you have such, are these solutions unique, right? Is there only one function that does it? That's pretty much never the case. You need some conditions, and so you want to ask, what are those conditions you might need for a unique solution to exist? So we'll talk about these first two questions a lot more in the next lecture, existence and uniqueness of solutions. And then, all right, so the solution might exist, but can you actually write it down? Is there some way to find it? Can you approximate it maybe? Or do you just know that it exists abstractly? Okay, so some techniques. So mainly the things we'll be focusing on in this first one are a big grab bag of tricks. So certain differential equations of a certain form you can solve in a certain manner, but as a whole, even ordinary differential equations, you're not really going to luck out on being able to solve those analytically by hand or anything. So really just a special class of differential equations will be ones that you can actually write out a solution by hand. But we'll be focusing on those for the most part. The second one, linearization. So for example, this pendulum equation back here, you can do some kind of small angle approximation where sine theta is approximately equal to theta for small values of theta. And then if you do that, this equation will actually be a linear equation, and that would be something you can solve. Whereas this nonlinear one, you cannot write down a solution for it. So that would be an example of some linearization, which is pretty useful. On the last lecture, we'll be talking about power series methods, which are somewhat similar. I mean, that's a method for solving certain differential equations where you write down the solution as a power series, and then I guess taking the first few terms of a power series would be an approximate solution to the full solution. And then finally, computers are super useful. So in practice, given a differential equation, computers are one of your best bets for actually being able to have some kind of solution. And there you can graph the solution, you could come up with approximate values at given points, things like that. So if you have any access to like MATLAB or Mathematica, that's pretty useful. You can always use Wolfram Alpha, it's useful as well. Okay, so let's start out talking about first order ODEs. We'll assume that nothing too crazy is going on. So the first derivative is the highest derivative that appears, and we'll assume that you can do some algebra to solve for dy dt as a function of t and y. Right, so not necessarily linear, although we will be working more on linear first order ODEs later. All right, if you do it this way, there's a nice thing that you can do, which is you can draw this slope field or direction field picture of your differential equation. And the idea is that given a point t comma y in the plane, you can plug it into this function, and then that tells you the slope dy dt of the unknown function you're trying to solve for, and you can represent that with an arrow, as we've done here. So you can do that, put in small arrows at every single point. So this is for this differential equation, dy dt equals y plus t. And so you'll have a picture with arrows at every point. And then the idea is these are the slopes so that your solution would need to satisfy. So a solution should be sort of following along all these arrows. So you can see here in green, blue, and red, these are solution curves to this differential equation. And so you can see they're not going to really be unique. There's going to be infinitely many solutions. However, if you pin down some kind of initial condition, for example, the value of y at t equals 0, so here we have y of 0 equals 0, y of 0 equals 1/2, and y of 0 equals minus 1/2. If you have this initial condition, then if you follow along the arrows, in this case, you'll end up with a unique solution curve. So talking about those big questions from earlier, in this case, yes, there will be infinitely many solutions, but the solutions will be unique if you specify some sort of initial condition. It doesn't have to be t equals 0 necessarily. If you pick a point, t0, and specify some y value, then flowing along these arrows, you'll get a unique solution curve. All right, so let's talk about how to solve these first order differential equations. In the first order case, you can actually solve a decent amount of them by hand, but still in the general case, it's hopeless. You're not going to be able to do that by hand. All right, so maybe one of the easiest classes of an example, you just have dy dt as some unknown function of t. And in this case, your derivative is some function. It doesn't depend on y at all, so you can just integrate both sides with respect to t, and that will give you the general solution. So here you can see when you take this indefinite integral, you end up with some arbitrary constant popping out, which is what you'd expect, right? Looking at this kind of slope field picture, there should be infinitely many solutions up to some kind of single parameter that can vary. In this case, maybe you could think about it as an initial condition that's varying. So we have this unknown parameter, capital C, showing up in the general solution. All right, so a slightly harder example is if dy dt is a function of t times another function of y, f of t times g of y. In this case, it's called separable because you're able to separate the variables to either side. So if you divide both sides by g of y, then you have 1 over g of y times dy dt on one side and f of t on the other side. And now you can just integrate both sides with respect to t because right here, the chain rule or u substitution or whatever you want to call it, taking this integral of some function of y times dy dt, that's the same as doing the indefinite integral of that function of y times dy. All right, so these are both integrals. Hopefully you're able to actually evaluate the integrals by hand, but if not, still you're a lot closer to a solution than you'd be just from an arbitrary differential equation. All right, so that's how to, and then if you can evaluate these integrals, you may want to do some algebra to explicitly solve for y as a function of t. That might not always be possible. Okay, so here's a pretty easy example. Dy dt is just some constant r times y. You might think of this as, for example, investing with continuously compounded interest, some fixed interest rate r. So here r is a constant. All right, so we want to move the function of y to the left-hand side. So in this case, we just divide both sides by y. We've got 1 over y dy dt is equal to r. And now we can integrate both sides. On the left side, we integrate 1 over y dy, and we end up with the natural logarithm of the absolute value of y. On the right-hand side, we're just integrating a constant, so we end up with rt plus c. And now in this case, we can explicitly solve for y as a function of t by exponentiating both sides. All right, so I've sort of skipped a couple steps here, right? So really going from here to here, we'd have something like absolute value of y exponentiating both sides times e to the rt plus c. And the idea, right, is using exponent rules. We can write this as e to the c times e to the rt. But c was just some arbitrary constant anyway, so we can replace this by some other arbitrary constant. And also, absolute value of y being equal to things, well, that means y is either equal to that expression or minus y is equal to that expression. So we'd have something like this. And then the idea is this plus or minus times e to the c, that's just an arbitrary constant. So we can just replace that with the c over here in the final solution. I guess that's also including a solution y is equal to 0 for all values of t, but you can see that does actually solve the equation here, right? If you plug in y equals 0 for all t, that is a solution. Right, the derivative of that is also 0, so you'd have 0 on both sides. Okay, so that's the solution to that differential equation, fairly easy. Okay, for a slightly harder case than separable differential equations, we can talk about first-order linear differential equations. So remember, that means that our differential equation, if we put everything onto the left-hand side and set it equal to 0, the left-hand side should be a linear function of y and dy dt, but not necessarily r of t. So in that case, we're allowed these coefficient functions that can vary with t. So p of t, q of t, and r of t, those can be functions of t, but dy dt and y have to appear as they're shown. All right, so if p of t is non-zero, then we can divide by capital P of t and put this equation into standard form. So here we've divided everything by capital P of t. So this lowercase p of t, right, that would be capital Q divided by capital P, and this lowercase q would be capital R divided by capital P. All right, so the idea to solve this one is that looking at the left-hand side, we have a sum of two terms, one of which involves y and one of which involves the derivative of y. And that's something that shows up when you use the product rule, right? So the product rule, if you have a product of two functions, the derivative of that will be this fg prime plus f prime g. So if one of the two functions in this product rule here is y, then you'll have one term involving y prime and then another term just involving y. So that's sort of what shows up in our differential equation. It's probably not going to be exactly a product rule to start with, but if we modify the entire equation by multiplying it by some unknown function mu of t, then we might be able to actually get the left-hand side to be a product rule expression like this. And in that case, we can directly integrate both sides, which more or less is the only way we know how to solve differential equations so far, is by doing some trick and then integrating both sides. So this is, again, the same kind of thing. So this mu of t is called an integrating factor because it allows us to solve the equation by integrating both sides. All right, so how do we find this unknown function mu of t is the question. So this is what our differential equation would look like if we multiplied it by some function mu of t. And we want the left-hand side to be a product rule involving with one of the functions being y. And if we look at this term here, this mu times dy of t, then the other function has to be mu, right? So the product rule of f times g, this is f g prime plus f prime g. So if y is playing the role of g, then looking at this first term, mu would be what needs to play the role of f, because that would be the fg prime t would be, this fg prime term would be mu times dy dt. All right, the other term in the product rule is d mu dt times y, and what actually shows up in our differential equation is mu times p of mu of t times p of t times y. And so that means in order for this to be a product rule expression, what we need is for d mu dt to be equal to mu of t times p of t. All right, and now that is exactly a separable equation, which we know how to solve. We move the mu term to one side by dividing, and then we can just integrate both sides. Okay, so divide both sides by mu, take an integral of both sides. Once again, we'll end up with a natural logarithm. In this case, it's the natural logarithm of the absolute value of mu. The other side will have the integral of p of t dt, and now we can take an exponential of both sides. In this case, we don't need to worry about any kind of plus c, so we don't need to worry about any of these arbitrary constants. So we don't need to include this plus c with our integral, or a c multiplying this exponential, because we just need one function mu of t that will allow us to solve our differential equation. So we can just choose, as long as we choose some function of mu of t that makes this left-hand side into some product rule expression, then we can just integrate both sides. So we're not looking for all the values of mu of t that do it. We're trying to find all of the solutions y of t, but this mu of t that helps us solve the differential equation, we don't need to actually know what all of the mu of t's are. We can just pick one that will let us solve the differential equation and go from there. Okay, so you find this mu of t, multiply the entire differential equation by mu of t as above, and then you can just integrate both sides. So that's the strategy. All right, let's look at an example. So here we're going to solve an initial value problem. What that means is that we're given a differential equation and an initial condition, and we're going to try to find a solution that solves it. And usually that will be unique. We'll talk about that more next time. Usually this is a single solution to an initial value problem like this. Okay. So here we want to solve this, but our first step is that we need to convert it to standard form. The reason for that is because this whole process that we went through of where we found this formula for the integrating factor mu of t, we started with a differential equation here in standard form. So we started with this standard form differential equation to do this process, right? Everything's in terms of this lowercase p of t, which was the standard form coefficient. So if we want to, use the work that we've already done, we'll need to convert this differential equation to standard form. So we divide both sides by lowercase t. And in this case, we'll see now that this coefficient, lowercase p of t, is 2 divided by t. And now, if we want to solve this differential equation, we'll need the integrating factor mu of t. So from the previous slide, we have this formula, that mu of t is equal to e to the integral of p of t dt. Here, our lowercase p of t is 2 divided by t, and so we'll be integrating that. That's 2 times the natural log of the absolute value of t. And now e to 2 times the natural log of absolute value of t ends up being t squared, right? This is, again, using some kind of exponent rules if you want, right? So e to the 2 times ln absolute value of t, that's the same as e to the ln of absolute value of t quantities squared, right? This is a exponent rule. When you have a product of two things in the exponent, you can use that as, like e to the a times b is e to the a quantity to the power of b. So that's what we're using here. And since e and the natural logarithm are inverse functions, that's the same as the absolute value of t quantity squared. But t squared is always positive already, so you can just get rid of the absolute value. All right, so the mu of t we need is just t squared. And so what we want to do is multiply the entire equation by t squared. Remember, we're multiplying the standard form equation by t squared, not the original equation. So that's why we end up with t squared times y plus 2t times y, t squared times y prime plus 2t times y is equal to 4t cubed. All right, and now we just want to integrate both sides. Okay, so here's where we were at from the end of the previous slide. And now we want to integrate both sides with respect to t. And by design, the left-hand side is a product rule expression. Specifically, it's the derivative of the quantity t squared times y. Right, so we have this first term. We leave the t squared alone and take the derivative of y. That would be this t squared times y prime term. And in the second term, we take the derivative of t squared, which is 2t, and leave the y alone, and that's the second term. All right, so that is indeed the derivative, a product rule derivative, like we wanted. And now we can just undo that derivative by integrating both sides with respect to t. So this left-hand side, we just end up with t squared times y. The right-hand side, the integral of 4t cubed, is just t to the fourth plus a constant c. And now if we want to solve for y as a function of t, we just divide both sides by t squared. So y is t squared plus c divided by t squared. All right, so this would be the general solution. So all solutions to the differential equation would have that form. But remember, we were trying to solve an initial value problem. So we want to specifically find the solution where y of 1 is equal to 2. Doing that's not too hard at all. We just plug t equals 1 into our general solution and solve for this unknown constant c. Okay. So that's what we'll do here. So the general solution, we have y is t squared plus c divided by t squared. So y of 1 is supposed to be equal to 2. And if we plug in y of 1 into this equation, this t squared is just 1. This other t squared is also 1. So we end up with 1 plus c. All right, so 1 plus c is equal to 2. That tells us that c is equal to 1. And so y plus t squared y is equal to t squared plus 1 over t squared. That's the solution to the initial value problem. And this solution is only valid for positive values of t. The reason for this is because we want the domain of our solutions to be connected. And of course, this is undefined at t equals 0, right? We have a vertical asymptote there. And we want a connected domain because of this whole idea back with the slope fields here. We want the information we're getting from this differential equation comes from us sort of following along these arrows. But if you go to a vertical asymptote off into infinity, you don't really have any more information that you can follow. Right? So certainly there are solutions that are defined for negative values of t. They're just not really related to the initial value problem we started with. Right? So certainly you could have some kind of IVP with like y of -1 equal to 2 or something like this would be defined for negative t. But that's not really related to the one we started with, right? Once we've gone off to this vertical asymptote, you could sort of have whatever values you wanted for negative values of t, but they're not going to be related to the original solution. Certainly there's no way you're going to get anything that's like continuous, that's continuing on from the positive values of t to the negative values of t because you have this vertical asymptote. Right, so that's the reason we're usually interested in a sort of connected interval of existence for our solutions. And I'll talk about that more in the next lecture. Okay, yeah, I think actually this y of -1 is equal to 2. Yeah, that is exactly the same function. This y equals t squared plus 1 over t squared is also the solution to this other initial value problem. But in that case, it would be only defined for negative values of t, whereas this one's only defined for positive values of t. So those are sort of solutions to two different initial value problems. So if you start at this negative value of t, then you'd have information about all the negative values of t, but no information about positive values of t because you're hitting this vertical asymptote coming up from the left. If you start at t equals 1, then you'd have this solution that's defined for all these positive values of t, but you don't have any information because you go to this vertical asymptote from the right at t equals 0. All right, so I think I will stop there, and next time we will talk about existence and uniqueness theorems, so two of those big questions earlier about when do solutions exist and when are they unique and how many conditions do you need to guarantee a unique solution.